Hello viewers, in today's session we are going to discuss an important problem from differentiability of functions, and here we are going to solve this problem where we have to prove that the function f of x, that is equal to mod of x minus 1 minus mod of x minus 2, is not differentiable at x is equal to 1 and x is equal to 2, right? So here we have to show that this function f of x, which is the difference of two absolute value functions, two modulus functions. The first one is mod of x minus 1 and the other is mod of x minus 2, is not derivable at x is equal to 1 and x is equal to 2, right? Now see, the domain of this function f of x is the set of all real numbers, right? And this function f of x is continuous for all values of x belonging to the set of real numbers, right? Because we know that mod function is continuous for all values of x, right? So here this function, that is mod of x minus 1, is continuous for all values of x. Similarly, this function, that is mod of x minus 2, is also a continuous function for all values of x, and overall this function f of x is continuous for all values of x, right? Belonging to the set of real numbers. But this function is not differentiable at these 2 points, right? This function is differentiable for all values of x belonging to the set of real numbers except these 2 points, that is x is equal to 1 and x is equal to 2, right? So here we'll prove that this function is not differentiable at these 2 points with the help of the concept of right hand derivative and left hand derivative, right? So we'll find out the right hand derivative and left hand derivative for this function f of x at x is equal to 1, and then for x is equal to 2, and then we'll conclude that this function is not differentiable. Now let us start. So now let us first define the right hand derivative and the left hand derivative. So the right hand derivative is defined by this limit, that is limit h tends to 0. We have f of a plus h minus f of a divided by h, and here the notation may be taken as r for the right hand derivative, and then we have f of here a positive, right? And the left hand derivative is defined by this limit h tends to 0, f of a minus h minus f of a divided by minus h, and here we have L for the left hand derivative, and here we write f of a negative, right? So let us now prove the non-differentiability of this function at this point, that is x is equal to 1 and x is equal to 2. So let us first take this point, that is x is equal to 1. So here we'll now take a is equal to 1, right? So let us first find out the right hand derivative and then left hand derivative. So the right hand derivative is now given by a limit, and here h tends to 0, and remember h is an infinitesimally very small quantity and it is always positive, right? And here we have f of 1 plus h because a is equal to 1, right? And here we have f of 1 and here we have h. So now we have limit h tends to 0. Now f of 1 plus h can be obtained by replacing x by 1 plus h in this function. So we have here a mod of 1 plus h minus 1, then we have 1 plus h minus 2, and we can now find out the value of f of 1 separately here. F of 1 is given by mod of 1 minus 1 minus mod of 1 minus 2. So this is mod of 0, this is mod of minus 1, and this is 0. And here mod of minus 1 is 1. So here we have 1, so that is equal to minus 1, right? So here we have f of 1 as a minus 1, and in the denominator we have h, right? So now we have limit h tends to 0, and here 1 and 1 get cancelled. We have mod of h, then here we have mod of h minus 1, and here we have plus 1. Minus and minus multiplied together, it gives us positive, and here we have h, right? Now see, we have just said that h is infinitesimally very small, and h is a positive quantity. So now let us make use of the definition of a mod function here. So mod of p is defined as positive p whenever p is a positive number that is greater than 0, and mod of p is 0 whenever p is equal to 0, and mod of p is negative p when p is less than 0, right? Now see, here we have mod of h, and mod of h is simply equal to positive h because h is greater than 0 due to this definition, right? And here we have a mod of h minus 1, right? Now see, h is infinitesimally very small, and it lies between 0 and 1. So this difference, that is h minus 1, is always going to be less than 0. That is, this quantity is always going to be negative, right? So due to this definition, that is mod of p is equal to negative p when p is less than 0. So here we can take p as h minus 1, and h minus 1 is negative, that is it is less than 0. So mod of h minus 1 is now equal to, due to this definition, we have negative of h minus 1, right? So we can now write here minus h and plus 1. So here we have now limit h tends to 0. Mod of h is simply positive h, and here we have negative of mod of h minus 1, which is equal to 1 minus h, right? So here we have 1 minus h plus 1 over h. So this is limit h tends to 0, and here we have h minus 1 plus h plus 1 over h. Now minus 1 and 1 get cancelled. We have limit h tends to 0. This is 2h over h. H plus h is 2h over h. H and h get cancelled. We have limit h tends to 0 and 2, right? And now this expression is independent of h, so the limit is simply 2, right? So the right hand derivative of this function at x is equal to 1 or a is equal to 1 is given by 2. So here we write the right hand derivative equal to 2. Now let us find out the left hand derivative. So now the left hand derivative is given by limit h tends to 0 f of 1 minus h. So we have 1 minus h, and here we have f of 1 divided by minus h. So we can now write limit h tends to 0. F of 1 minus h can be obtained by replacing x by 1 minus h. So we have a mod of 1 minus h minus 1. Then we have here 1 minus h minus 2, and f of 1 is minus 1. And here we have minus h. So let us simplify this expression. So here 1 and minus 1 get cancelled. So we have mod of minus h, and here we have mod of minus h minus 1, right? And here we have plus 1, and here we have minus h, right? So now let us once again make use of this definition of mod function. Now see, here we have a mod of minus h. Now h is a positive quantity, so negative h is less than 0, right? Because h is a positive quantity, right? And minus h is less than 0, that is minus h is negative. So due to this definition, mod of p is equal to negative p. So mod of minus h is equal to minus, and here we have minus h because p is minus h. So this is plus h. And similarly here mod of minus h minus 1 is given by negative of minus h minus 1, because this quantity, that is minus h minus 1, is a negative quantity because here h is positive, right? So again, due to this definition, we have mod of minus h minus 1 is negative of p. P is minus h minus 1. So here we have plus h plus 1. So now we have limit h tends to 0. Here we have simply h, and then we have here h plus 1 over minus h, right? So now we can write limit h tends to 0, and here we have h minus 1, and here we have plus 1, and here we have minus h. Now we can see that the numerator is 0 because h and minus h get cancelled, 1 and minus 1 also get cancelled, and here we have 0 over minus h, that is equal to 0, right? So the left hand derivative is equal to 0, right? So now from this discussion, we have seen that the right hand derivative is 2 and the left hand derivative is equal to 0. And the right hand derivative is not equal to left hand derivative, that is 2 is not equal to 0. So this function f of x is not differentiable at x is equal to 1, because for a function to be differentiable at a given point in its domain, the right hand derivative and the left hand derivative both should exist, and they should be finite, and moreover they should be equal to each other. But in this case, the right hand derivative is not equal to the left hand derivative, that is 2 is not equal to 0, right? So the function is not differentiable at x is equal to 1. So now let us consider this point, that is x is equal to 2. So now consider this point, that is a is equal to 2. So now the right hand derivative is given by limit h tends to 0, and we have f of 2 plus h minus f of 2 divided by h. Now let us first find f of 2. So f of 2 is it can be obtained by replacing x by 2. So we have mod of 2 minus 1, and then we have 2 minus 2. So mod of 2 minus 1 is mod of 1, here mod of 0, and this is 1 minus 0, that is equal to 1. So f of 2 is equal to 1, right? And here we have limit h tends to 0. F of 2 plus h can be obtained by replacing x by 2 plus h. So we have mod of 2 plus h minus 1 minus 2 plus h minus 2, and here we have f of 2, that is 1, and here we have h. So now simplifying this expression, we have mod of this is 2 minus 1 is 1, 1 plus h minus 2 and minus 2 get cancelled, and we have here h, right? So now again here we have to use this definition. So mod of 1 plus h is simply equal to positive 1 plus h, because h is a positive quantity, 1 is also a positive quantity, so 1 plus h is always going to be a positive, right? And due to this definition, when p is positive, p is greater than 0, mod of p is equal to a positive p. And similar is the case with mod h, and mod h is equal to a positive h, because h is a positive quantity, right? So now we have here limit h tends to 0, and here we have simply 1 plus h, here we have simply h and minus 1 over h, and here 1 and minus 1 get cancelled, h and h get cancelled, and we have limit h tends to 0, and here we have 0 over h, and that is equal to 0, right? So the right hand derivative of this function at this point is given by 0, right? So now let us find out the left hand derivative. So now the left hand derivative is defined by this limit h tends to 0, and here we have f of 2 minus h minus f of 2 divided by minus h, right? And we can now write limit h tends to 0. F of 2 minus h can be obtained by replacing x by 2 minus h. So we have mod of 2 minus h minus 1, and then mod of 2 minus h minus 2, and here we have f of 2 that is equal to 1, and here we have minus h. So let us simplify this expression. So we have 2 minus 1 is 1, so we have 1 minus h, mod of 1 minus h, and here minus 2 and 2 get cancelled, and mod of minus h, and here we have minus 1 over minus h, right? Now let us consider mod of 1 minus h. Now again due to this definition, now see 1 minus h. 1 minus h is going to be a positive quantity, because 1 is greater than h, right? And h is a positive quantity, so 1 minus h is always going to be positive, that is 1 minus h is greater than 0. So mod of 1 minus h should be equal to positive 1 minus h, and here we have mod of minus h, and mod of minus h is simply equal to here a negative of h, that is positive h, because h is greater than 0 but minus h is less than 0. So here minus h is less than 0, so due to this definition, mod of minus h is equal to a negative of p. So negative of p is minus h, so we have positive h. So now we can write here limit h tends to 0, mod of 1 minus h is simply 1 minus h, and here we have mod of minus h is simply h. So here we have h and minus 1 over minus h. So we can now write limit h tends to 0, and here we can see that 1 and minus 1 get cancelled, and minus h and minus h, it becomes minus 2h, and here we have a minus h, right? And here negative and negative get cancelled, h and h get cancelled, and we have limit h tends to 0, and here we have 2, and this term is independent of h, so here we have simply 2. So the left hand derivative of this function at x is equal to 2 is 2. right? So here we conclude that although the right hand derivative and the left hand derivative both exist and they are finite, but they are not equal to each other. That is, a right hand derivative is not equal to a left hand derivative. 0 is not equal to 2. So this function is not differentiable at x is equal to 2, right? So viewers, this is how we can prove the non-differentiability of this function at these 2 points. Hello viewers, in today's session we are going to discuss another important application of vectors, and in this session we are going to prove an important result from trigonometry, that is sine of alpha minus beta is equal to sine alpha cosine beta minus cosine alpha sine beta. And here we'll prove this important result from trigonometry using the concept of vector product of two vectors, right? That is the cross product of two vectors. So let us see how we can prove this result using the concept of product of two vectors. So let us start. So now here we'll consider y-axis and x-axis, right? So this is x-axis, this is y-axis, and here we have the origin. Now let us consider 2 points on this plane, that is x or y plane, and here we have the point A, and here consider another point B, right? So let us form the vectors, vector OA and vector OB. So here we have the vector OA, and here we have the vector OB, right? So now let us consider this angle, that is angle XOA is equal to alpha, and this angle, that is angle XOB, as beta, right? So here we'll take this vector, that is vector OA, as vector A, that is here we have vector A, and we'll take a vector OB as vector B. So here we have a vector B. Now here along the OX axis we have the unit vector, that is I cap, and here along the OY axis we have the unit vector, that is j cap, right? And O is our origin. So now here we have angle XOA as angle alpha, and this angle that is XOA is alpha, and angle XOB is beta. So that the difference of the angles alpha and beta is given by this angle, that is alpha minus beta, that is our angle BOA. So angle BOA can be written as angle XOA minus angle XOB, that is equal to alpha minus beta. So let us take angle BOA as angle theta. So theta is alpha minus beta. So here we have to prove that the sine of the difference of the angle alpha and beta is given by this expression. So now let us draw perpendiculars to this axis, that is x-axis, from this point A and this point B. So here I will drop a perpendicular to the x-axis, and here we have the point say E, right? And from here we drop a perpendicular to x-axis, and here we have the point say F, right? So now we have two triangles, that is triangle uh, OE and A, and here we have the triangle that is OF and B. So now in triangle OE and A, we can write cosine alpha is equal to, that is base over hypotenuse. So we have OE over OA, and we can now write OE over A. So the magnitude of the vector OA is denoted by simply A, right? So OE is now equal to A cos alpha, right? And if we take sine alpha, then we have perpendicular over hypotenuse. So we have AE over OA. So we have AE over A, so that AE is now equal to A sine alpha, right? So the coordinates of this point A can now be written as OE comma AE, that is OE is the abscissa and AE is the ordinate. So we have here A cos alpha comma A sine alpha, right? And similarly in this triangle we have cosine beta is given by OF over OB, and OF is here we'll write OF, and OB is the magnitude of vector OB, that is simply a B. So we have OF is equal to B times cosine beta, and similarly sine beta is given by perpendicular over hypotenuse. So here we have FB over OB, and FB over OB. OB is the magnitude of vector uh, OB. So here we have B. So FB is now given by B sine beta. So now the coordinates of this point B can be written as OF comma FB. OF is B cos beta, and here we have B sine beta, right? So now we can write vector OA and vector OB in terms of these coordinates. So now let us apply the triangle law of addition of two vectors to this triangle, that is OEA and OFB. So in triangle OEA, we can write this vector, that is vector OA, as the sum of vector OE, that is along x-axis, and vector EA, right? So here vector OA is equal to the sum of vector OE and vector OA. So vector OA is vector A, and OE can be written as A cos alpha, and this is along x-axis. So here we have I cap, and EA is given by A sine alpha, and this is along the y-axis. So here we have J cap, right? So this is the component of this vector A along x-axis, and this is the component of the vector A along y-axis. So we can now write vector A is equal to A times, here we have cos alpha I cap, and here we have sine alpha and J cap, right? Taking A as common. Now in triangle OFB, we can similarly write vector OB as vector OF plus vector FB. B. So this is the component of vector OB along x-axis, and this is the component of vector OB along y-axis, right? So now we have here a vector B, and OF can be written as B cos beta, and here we have I cap, and here we have vector FB as B sine beta, and here we have j cap. So now we can write vector B as taking B common here. We have cosine beta I cap, and here we have sine beta and j cap. And remember, A represents the magnitude of vector A, and B represents the magnitude of vector B. So now let us form the vector product, that is B cross A, right? So now let us find out the uh, cross product of vector B and vector A. So here we have B and cos beta I cap, then we have sine beta and j cap, and then we have here A and cos alpha I cap and sine alpha and j cap. So now here we have AB, and now we have to take the cross product of these two vectors. So we can now write here, first we'll multiply this term with this one. So we have cos beta times cos alpha, and here we have I cross I. So here we have I cross I, then we have cos beta, and here we have sine alpha, and we have I cross j, right? That is the vector product of vector I with vector j. And then we have sine beta times sine beta times cosine alpha, and we have a j cross vector I, and then we have sine beta and sine alpha, and we have a j cross j, right? So this is the vector product of these two vectors. So now here this term is 0, and this term is also equal to 0, because I cross I is a 0 vector, right? And similarly j cross j is also a 0 vector, right? Because we know that the cross product or the vector product of the vector with itself is a 0 vector. So these two terms are 0. So we have now a B cross A is equal to AB, and we are left with only this term and this term, right? Now here we have I cross J, right? So I cross J is given by say vector K, right? And this vector K is perpendicular to the plane containing vector I and vector j, right? So I cross j is equal to K, and here we have a j cross I, right? So j cross I can also be written as minus I cross j, because we know that say A cross B is equal to minus B cross A. So if we interchange the vectors, we have a negative sign over here. So we have j cross I is equal to negative of I cross j, and I cross j is vector k. So here we have minus k cap. So here it is important to note that the cross product of I and j vectors is equal to vector k, right? And these are unit vectors. And here this vector k is perpendicular to the plane containing a vector a and vector b, or vector I and vector j. So now we can replace I cross j by k cap, and j cross I by minus k cap. So we have now cos beta, then we have sine alpha, and here we have k cap, and then we have sine beta cos alpha, and here we have minus k cap. So now we can simplify it. So we have AB, and now we can write here sine alpha, then we have cos beta, and here we have the negative sign, this negative sign over here, and we have cos alpha sine beta, and we can take here k cap as a common, right? So here k cap it appears in both the terms, right? And this negative sign can be taken over here. So we have the product of these two vectors, vector b and vector a, given by this expression. So now let us take this expression, entire expression, as equation 1. And now from the definition of cross product of two vectors, we know that b cross a is also given by the magnitude of vector b, magnitude of vector a, and here we have sine of the angle between vector b and vector a, that is given by alpha minus beta, or theta, right? So here we write theta, and here we have a vector, unit vector, that is perpendicular to the plane containing a vector b and vector a, right? And the vector, or the unit vector, which is perpendicular to the plane containing vector b and vector a, is given by k cap, right? So we have now the definition of the cross product of vector b and vector a given by this expression. Now we can replace the magnitude of vector b as simply b, and magnitude of vector a by simply a, and here we have sine theta and k cap. So we have a b cross a is given by this expression, right? So we can also write it as b cross a is equal to ab sine, and theta can now be replaced by alpha minus beta, and here we have k cap. So this is our equation 2, right? So now if we write this equation over here, then we have b cross a is equal to AB, and here we have sine alpha minus beta, and here we have k cap, right? So this is our equation number 2. So now if we look at these two equations, then the left hand side are same, and here we have the right hand side, and here also we have the right hand side. So now if we compare the right hand side of both these equations, then here we have AB, here we have AB, that is the product of the vectors a and vector b, and here we have the vector, the unit vector, that is k cap, which is perpendicular to the plane containing vector a and vector b. So now this expression, that is sine alpha minus beta, should be equal to this expression, that is sine alpha minus beta is equal to sine alpha cosine beta minus cosine alpha, and here we have sine beta, and this is our desired result. So comparing equation 1 and equation 2, we can see that sine alpha minus beta is equal to this expression, right? And this is how by using the concept of the vector product of two vectors, we can easily prove this important identity or formula from trigonometry, and similar results can also be proved by using the concept of the scalar product of two vectors or the cross product of two vectors.